Hi, and welcome to the Coursera class, An Introduction to Statistical Inference as part of the Data Science specialization. My name is Brian Caffo. I'm a professor in the Department of Biostatistics at the Johns Hopkins University, and I'll be your instructor. I'm joined by my co-instructors Jeff Leake and Roger Peng, who are also in the Department of Biostatistics. Statistical inference is the process of drawing formal conclusions from data. In our class, we're going to define formal statistical inference as settings where one wants to infer facts about a population using noisy statistical data where uncertainty must be accounted for. So in fact, whenever someone says something like the probability that something occurs, or gives a confidence interval or a hypothesis test, they are performing statistical inference. This class will teach you not only how to do these things, but why to do them and what are the inherent limitations in the various forms of inference. A good example of statistical inference is trying to predict who's going to win an election. Basically, in every major election, pollsters would like to know ahead of time who is going to win. Hence, the target of estimation, the estimand, is clear, the percentage of people in a particular group who will vote for each candidate. But we can't poll everyone, and even if we could, some people might change their vote prior to the election. And so we need some method for being able to draw conclusions from the data that we have and also quantify the uncertainty associated with having made that conclusion from an incomplete set of data that may change over time. This is a formal statistical inference, perhaps the most famous version of a formal statistical inference. In this case, the way in which inference tends to be performed in this particular set of problems is to draw an analogy with a box with colored balls in it, let's say two colors, white and red, that you get to mix up the balls and draw a certain number of them. It is by this simplified version of the problem with well understood mathematics that we are able to perform inference. Therefore, to perform inference, you need to understand how the assumptions of how your data was collected relates to this simplified setting with the balls in the box. A fairly important example of statistical inference occurred with the Women's Health Initiative, where they investigated hormone replacement therapy. Prior to the study, hormone replacement therapy was a standard care for postmenopausal women, and this clinical trial investigated its efficacy. It was a clinical trial in that they randomized the treatment, hormone replacement therapy, to a group of people while randomizing a placebo or standard of care to another group of people. The randomization then balanced unobserved covariates, hopefully, so that inferences would likely not be contaminated by them. However, based on a statistically based protocol, the study had to be stopped because HRT was shown not only to be not effective, but also have a negative impact on several key health outcomes. So there's several interesting things to discuss for this class. One was the important question of this, that the study was designed to investigate. Is HRT effective? And to discuss why did they do randomization, how would one answer a question like that, how would one formulate the problem, and how would one perform the statistical inference. There's a second question that's actually much harder that we will not discuss, which is how long should we continue the trial in the presence of contrary evidence? This is a very challenging question and depends on many factors, including morality, how long can we give a treatment relative to a certain amount of evidence against it to otherwise healthy people, versus how long can we run a trial, how can we stop a trial just based on random fluctuations that one would expect to occur with low sample sizes. So one must balance between these considerations if you want to actually achieve the evidence required to make medical decisions. So question 2 is in fact a quite difficult and challenging question, and question 1 is actually a fairly challenging question, but one that we'll be able to make significant headway at in this class. And I would say this is by no means the end of this topic in terms of discussing hormone replacement therapy in the medical literature. So this JAMA paper in 2002 is one that you can refer to, but then there's been, of course, over a decade of work on this, and so certainly don't view this discussion as a component of making your own personal medical decisions, given that the recommendations have been refined quite a bit since this study. Here's another interesting and kind of funny example of statistical inference. In the area that I work in, so-called functional magnetic resonance imaging, they stick people in an MRI scanner and they have them do a task. And as they do this task, they record magnetic resonance images, and then they have them say, not do the task for a little bit, and then they do the task for another little bit, and then they not do the task for a little bit. They compare the times when they're doing the task, the images when they're doing the task to the images when they're not, and they look and they find areas that are then activated relative to the task. As a simple example, when someone's performing some motor function like tapping their finger, when you compare that to the times when they're not tapping their finger, the motor area of the primary motor area lights up exactly like you would expect in the area associated with your finger. This initial discovery has led to mountains of paper on so-called mapping the brain and generalizations to harder areas, such as trying to investigate the ways in which different areas of the brain communicate with one another using the same technology. At one point, some investigators wanted to illustrate the ways in which people can obtain false positives in this area by in fact conducting a study not with a person in the scanner but by sticking a dead salmon into the scanner and performing a rote style analysis. There are many interesting aspects to the way in which they conducted the study, and many ways in which they highlight failings of performing lots of hypothesis tests without accounting for multiple comparisons. In this case, if you do lots of hypothesis tests without accounting for multiple comparisons, you in fact see activation in this dead salmon, which of course, as far as anyone could tell, really doesn't have any sort of brain activation since it's a dead salmon. So at any rate, it highlights something we are going to talk about in the class, is how do you perform inference when you're performing lots and lots and lots of hypothesis tests, and hopefully you won't get caught in declaring brain activation in a dead salmon. I don't think you would anyway, but after this class you for sure won't. I hope I've convinced you that statistical inference is a key subject for a modern data scientist. It is only through the formalism of statistical inference that you can create parsimonious new knowledge about a population from noisy, uncertain data. The examples that we covered illustrate some of the important concerns in statistical inference. For example, is the sample representative of the population you'd like to draw inferences about? In our polling example, if we had a very biased sample, then our conclusions would not be representative of voters on election day, and our results, of course, would probably not pan out. In our HRT example, we talked about a clinical trial. The clinical trial randomization tries to balance unknown and unobserved variables that might contaminate our conclusions. Something we did not talk about but might be a problem is missing data. In our HRT example, what if by virtue of not being blinded, this was not the case in the HRT example, but imagine if you did a clinical trial and those who received the placebo were aware that they received the placebo, and the sickest in that group decided to drop out of the trial because they were going to pursue other therapies that precluded them from being in the trial. Then at that point, your conclusions might be very biased because in the placebo condition, the sickest people were all dropping out. Missing data has created a systematic bias that is unrelated to the mechanisms that's related to the mechanisms being studied. The next bullet point is actually quite difficult. What randomness exists in the data and how do we use and adjust for it? Randomness can arise in several ways. For example, the randomness from the randomization scheme, the randomness from the way in which the data is sampled, and the randomness from the assumption that large numbers of unobserved things accumulate in ways that can be modeled as if they are statistical randomness. All of those represent kinds of things we're willing to model as random or we explicitly know are random in the case of randomization. The final bullet point is, are we trying to estimate some underlying mechanistic model? If so, we can build that model into our statistical inferential probability model, and that's often a good way to go. So the fundamentals of statistical inference requires navigating these set of assumptions and tools and subsequently thinking about how to draw conclusions from the data and understanding how robust your conclusions are to those assumptions. Statistical inference is a very deep area that can take decades to learn. However, in this class, we're going to give you some of the very fundamentals. Let's go through some examples of goals of inference. In this class, not only will we estimate things, we'll actually formally define the estimands. So our sample mean will be the estimate of a population mean. So in our polling example, we want to estimate the proportion of people who will vote for a candidate on election day among people who are actually going to vote on election day. However, we're going to have a potentially biased small sample that we're going to have to do that with, and so we want to quantify the uncertainty in that small sample and acknowledge the potential biases and acknowledge how our assumptions has played into both our estimate and how we've quantified the uncertainty in that estimate. We might want to determine whether a population quantity is a benchmark value. Is the treatment effective? And in this point, I'm alluding to a topic called hypothesis testing. We might want to test the hypothesis: is the proportion of people who respond to treatment equal to the proportion of people who respond to a control therapy? We might want to infer a mechanistic relationship when quantities are measured with noise. For example, what is the slope of Hooke's law? If you are a physicist and you want to infer Hooke's law from a set of sample springs that you have, you of course won't get things falling exactly perfectly on a line. You might want to infer that line using the tools of inference, adjusting for the uncertainty given that there's noise in your measurement. We'll talk a lot about how exactly to do that in our regression class. We might want to determine the impact of a policy. So for example, if we reduce pollution levels, will asthma rates decline? And as an example in that case, we might evaluate that question by doing something like a natural experiment, looking at places where pollution levels decline naturally and trying to evaluate our assumptions as to the comparability of the population before the pollution levels decline to the population after pollution levels decline. As an example, you might have a place where a major pollutant type company moved and set up shop somewhere else so that the pollution rates declined before and after the company was there, and you could look at asthma rates before and after. Of course, you would have to assume or evaluate whether or not the subjects that were there before the company left and after the company left are comparable among other characteristics other than asthma rates. That's the kind of questions we're going to answer. Again, we're going to talk about the other effects and dealing with confounders a lot more during our regression class. Finally, in 5, I talk about a very generic statement. Whenever anyone talks about the probability that something occurs, where they've estimated that probability from data, they're making an inference. They're talking about a population probability. Okay, and that is again something that we need to have a formal framework around. If you ever use the word probability, you need to know the topics in this class. Let's talk about some tools of the trade in inference. Randomization is an example tool of the trade whereby you're interested in balancing unobserved covariates that may contaminate your inference. So in the HRT example, they randomize the treatment and placebo to make the groups as comparable as possible. In random sampling, we're interested in selecting subjects or units that are as representative as possible to the population that we're interested in making inferences about. That's, for example, key when you're doing polling. You want the people that you poll to be as representative as possible as the people who are going to vote on election day. Sampling models are concerned with creating a statistical model for the sampling process. The most common model is so-called IID, or independent identically distributed. This model can be highly warranted, for example, when you've conducted random sampling, or it can be highly suspect in other cases. And a lot of times we do not have much control over the sampling process, so our sampling model is made, but at least after this class we'll be wide-eyed about what entails in these assumptions. Hypothesis testing is an inferential technique where we're interested in making decisions. You have two hypotheses and you treat one as if it was the status quo, and you'd like to see if you can collect enough data, or if the data presents enough evidence to knock you off that status quo. That's so-called hypothesis testing or null hypothesis testing. Confidence intervals are a related topic, and we'll show in this class exactly how related, which is concerned with quantifying uncertainty in estimation. So when you get a mean, that is an estimator. It has an estimand. How well does it do in estimating that estimand in the terms of uncertainty? Probability models are the formal connection that occurs between a data and a population of interest. So generally you do not know the probability model, and so they are either assumed or approximated. But if you want the formal way in which you connect the data to a population The most common way of doing that is via a probability model. Study design is the process of designing experiments. So, for example, you might design your experiment to make your inferences as tight as possible, to make it as likely as possible that you would reject the null hypothesis if in fact the null hypothesis is false. You might design your study via randomization to balance unobserved covariates, and you might design your study with random sampling so that your population that you're studying is as representative as possible of the population that you're interested in. So study design is the process of combining these things in order to get the study that you want. Non-parametric bootstrapping and permutation testing, the last 2 points here, are very data-centric inferential techniques. Non-parametric bootstrapping is useful, for example, for creating confidence intervals, but with minimal assumptions where you live very much so in the data while you're doing it. Same thing with permutation testing. So there's a giant bifurcation in the way that people think about inference in the division between frequency and Bayesian thinking on inference. This is just one of the many ways in which inference is approached. And in fact, I think hopefully, at least on the previous slide, you can see that there's many different factors to think about when thinking about inference, and the Bayes versus frequency discussion is only one of those many factors. In this class, we're mostly going to think in terms of frequency-style inference and frequency-style probability. Here, by frequency probability, I mean the long-run proportion of times an event occurs in independently identically distributed repetitions. So for example, when I roll a die over and over and over again, I'm going to assume that I get a 1/1/6 of the time, and that's a frequency probability. Frequency inferences uses frequency interpretation of probabilities to do things like control error rates. So you might say, what should I decide given my data controlling the long-run proportion of mistakes I make at a tolerable level in independent repetitions of this experiment? Even if you only get one repetition, we're calibrating our error rates relative to the idea of independent replications of the experiment. That's how we're going to teach most of the specialization, and particularly the inference part of this class. Being data scientists, in addition to these classic treatments of probability and inference that we're going to go over, we're also going to consider some inferential strategies that rely heavily on the observed data, like bootstrapping and permutation testing. These are tools that data scientists use a lot. But as probability modeling is going to be our starting point, we're going to first build up basic probability. So in the next lecture, we'll cover probability. At a fairly high level, I might add, because I think it's important for data scientists to have a good foundation in probability and inference. That's why this class, I think for many people, is the hardest class in the series. However, we're going to omit lots of topics of inference that would be covered if you were to, for example, get a master's degree in statistics. So, as an example, we will not cover explicit use of random sampling in inferences in the way in which some sample survey and polling, people who conduct polls use random sampling as part of their inferential strategy. Same thing with explicit use of randomization inference. If you want more on that, you might look into the literature on so-called causal inference. Bayesian probability and Bayesian statistics we won't cover too much. Missing data, we will not cover too much, but again, it's a very important topic. Study design, we'll cover basic sample size calculations, but other than that, we're not going to cover too much on study design. So welcome to the statistical inference class as part of the data science specialization. We're really glad that you enrolled in it. Many students find statistical inference to be the most difficult class of the specialization, and with good reason. Inference is the most difficult topic in the specialization by far. I've been studying inference now for over 15 years, and I feel like I learn something new every day. However, inference is a key component of being a data scientist. If you don't understand statistical inference, then you really don't understand statistics. And without it, there is no way that you will be able to generalize beyond your data in a way that's meaningful. And so we really look forward to trying to get you started on the road to understanding this very important topic.